It's fine with me.
So I think it's a good time to start and to welcome Sebastian Grieninger from Stony Brook University on beautiful Long Island, who will speak about temporal entanglement entropy as a probe of renormalizing group flow. So thanks for coming, at least virtually, and the stage is all yours.
Can you make this full screen?
Yeah, thank you very much for giving me this opportunity to speak about my work. And this work was done in collaboration with Dima Katsev and Kazuki, who are also both at Stony Brook University. Yeah, and as I said, the talk is pretty short, so feel free to interrupt and discuss with me at any point. So I have some results, but I focused more on motivation and what I'm interested in and future directions. So maybe we can discuss about like what we could do in the future, and maybe some of you are interested in some of the things.
I like this because, I mean, results in talks are completely overrated.
Yeah.
In fact, one of the best talks I've ever seen, I may say this because you have a few slides, was when somebody submitted a talk on something extremely important, namely, are there self-correcting quantum memories in dimension 3 or less, which are stabilizer?
Courtney Brill?
Settings, exactly, Courtney Brill. And he had this wonderful construction with like fractals. But then before he, like after he had submitted and before he went, he found out it was completely wrong. And then he went on stage and said, like, I have good news and bad news. The bad news is I have no talk, I have no results. It's wrong. But then say good news, I'm still here, so we can still use the time together productively. So here's my ideas. But they're wrong. What can you say, guys? Anyway, thanks for this.
Okay, so I want to talk about momentum space entanglement, and it's conceptually clear what it is, but for me it's very hard to picture or draw a picture. So I asked AI to draw a picture, and this is what I got. I think the red color here is supposed to be infrared and blue is UV. So I'm not sure how accurate it is, but it's at least some picture to show. But yeah, maybe let me get started. So if we have some bipartite system, A and B, so then we can measure the degree of quantum correlation of that subsystem A with the rest of the system. And that's entanglement entropy. The entanglement entropy can tell us about how much quantum correlation that subsystem has with the rest. And we can define the entanglement entropy as a von Neumann entropy of the reduced density matrix, and the reduced density matrix rho A is just where I integrate out the rest of the system. So I trace over the rest of the system. And if we think about any kind of real physical system, then usually we don't have access to all the degrees of freedom. We only have access to some of the degrees of freedom. And usually what we can measure in experiments, it's some kind of low energy and low wavelength description. So all the high energy degrees of freedom are usually not universal. They are not accessible to experiment. We just see some effective theory at low energy. If this theory is now interacting, then that means that these low energy degrees of freedom, they are entangled with the high energy degrees of freedom that we don't have access to. So what's happening is that the low energy degrees of freedom should be described by some form of density matrix, because we are tracing over all the high energy degrees of freedom that we can't observe. We only have partial information. And in that density matrix, we trace out energy scales. So this is some sort of momentum space entanglement. We integrated out all the UV degrees of freedom. This makes sense intuitively, but you might not be that familiar with it. One description that's more familiar is if you had any QFT course, you looked at, you defined a QFT as that Wilsonian procedure. And what you're doing is some coarse graining. So if you coarse grain to some more coarse grained prescription, you trace out the fine degrees, so the high energy degrees of freedom, and you end up with an Wilsonian effective action. And there's already a problem. So in textbook treatments of
So can I
renormalization,
ask a question already
Yeah.
on the setting, just to be sure that I am getting it? So, I mean, sure, you have a Bosonic system, a many-body system, right? And then if they are unentangled, so harmonic oscillators, if they're interacting, then they start talking to each other, and you're tracing out inaccessible high energy degrees of freedom, correct? And this A mentioned above is not some real space A
yeah, it's not some real space.
but these are the degrees of freedom we're interested in. So the A is like the low energy degrees of freedom. You trace out the rest and you consider momentum space entanglement in a way.
Yeah, in the case, yeah, in the case of momentum space entanglement, the rho A, the interval A is low momenta. So yeah, the low energies. Exactly. Okay, yeah, if you look at the textbook treatments of renormalization, then there's a problem, because if you do that kind of coarse graining, you just coarse grain. You don't take into account that there's some entanglement between UV and IR. You just get rid of the degrees of freedom. And in real space, there's something wonderful. That's the multi-scale entanglement randomization ansatz. And if you coarse grain in real space with the mirror, then you have those disentanglers, and the disentanglers, they remove the short range entanglement. So you preserve entanglement during the coarse graining steps. And I think it would be very interesting to think about analogs for that in momentum space, and really work out randomization in a way that you optimize it, so that you take into account that your momenta are entangled, and when you coarse grain, you should disentangle them between the different coarse graining steps. So do you see this thing here?
Yes.
Yes.
Maybe I can hide it somehow.
Oh, no, we don't see it.
You don't see it. Okay.
He meant the window.
Which window?
The window of speakers that's appearing on his screen.
Yeah, there's some window that's partially blocking the slides, but okay.
No, we are, there's nothing blocking. Or this can happen. I've seen like the WebEx has that feature that when you have a window, it's not showing the window, but there's an irritating white spot at this place. It's a bit irritating. I was
Is it better now?
Yeah, it's fine. It's fine.
It was never bad.
Okay. Yeah, now I moved it out of the way for me. Yeah, it's from Zoom, and I only shared my PDF, so you probably don't see it, but I do see it. Okay. So let's talk about possible applications of momentum space entanglement. So one is thermalization. If I bring my system far from equilibrium, like I collide some heavy ions, or I have some condensed matter system where I abruptly change one of the couplings, then my system is far off equilibrium. And when I want to thermalize, there are many different energy scales involved. And they all interact in complex ways, and they're all entangled. So high energy degrees of freedom are entangled with low energy degrees of freedom. And the question here is, how does the entanglement between different scales affect thermalization? And I'll say more about that in a slide. And also, if we think about heavy ion collisions, then we have those jets that are coming out when the heavy ions collide, and the infrared region of those jets can be viewed as an open quantum system that's entangled with the rest of the system. And people started to recast the pattern evolution equation in terms of momentum space entanglement. So they're trying to use momentum space entanglement to describe the evolution of that jet and how it thermalizes. When we
Can I ask another question? I mean, but you steer like, I mean, how many questions you want, because it can also be annoying. When you say thermalization, I mean, do you mean like dynamical thermalization? In the sense you start out in some low entanglement state, you wait, and then for most times it will locally in momentum space look equilibrated and thermalized, or what do you mean? You probably mean this, right? You look at your
I just do something to my system. It's very, very far from equilibrium. I want to see how, and especially I want to understand why it thermalizes.
Okay.
Yeah, I'll say something about that on the next slide. in cosmology, if we think this, we can say the same about the state of the early universe, particularly during inflation and the entanglement properties of fluctuations. So the early universe was also some highly non-equilibrium state, and then we start expanding. We go from high energy to lower energies. And if we analyze cosmic microwave background radiation, then those different modes are analyzed by momentum scale. And there it's also crucial to note that those different modes at different scales are entangled. And it would be interesting to understand what the effect of momentum space entanglement is on that whole spectrum. And about the last point, I will also say more later what maybe we could use momentum space entanglement for temporal entanglement of qubits, or in quantum information, there are many codes that work in momentum space. Maybe there's a way of using it to optimize those codes. Yeah, why am I interested in momentum space entanglement? So for one, it's really fundamental to to any interacting quantum field theory. Since their degrees of freedom, they are necessarily entangled in momentum space if it's an interacting theory. And if I go to weakly coupled QFTs, then I can draw my Feynman diagrams, and there's a one-to-one relation between energy and the momenta of single quanta. They're linked. I can coarse grain, and it's very well defined how to put a momentum cutoff and how to trace out the high energy degrees of freedom. However, if I'm in a strongly coupled system that doesn't have any quasi-particle excitations, then it's much harder to have some notion what the momentum cutoff actually is. And I think to define this properly, we should have some Wilsonian definition of momentum space entanglement, because there we can clearly define what is the momentum cutoff. I mentioned thermalization, and I think thermalization could be the consequence of momentum space entanglement, or of entanglement in general, as opposed to scattering. In heavy ion collisions, or in general, if a system thermalizes, then the entropy of the final state is maximal. And where does all that entanglement come from? And it could be coming from the entanglement between different scales. And while my system thermalizes, I'm integrating out those higher energy degrees of freedom, and I end up with a low energy description. So I traced out a lot, I end up with high entanglement. And in particular, or at least I want to try to show that momentum space entanglement can actually lead to dissipation. So it's responsible for thermalization. And you can derive hydrodynamic equations of motion from momentum space entanglement. So hydrodynamic is some effective low energy description of your system that's based on the symmetries. And what I want to show is that it's
But
really...
can I ask another question?
Yeah.
And model law, I mean, you just stopped me.
Yeah.
I mean, when you say large amount of entropy, that's of course true. I mean, in a very thermal state, it's obviously by definition the maximum entropy state given the energy expectation, like trace of rho h in a way. But of course, there's also other ways to having large entanglement without being purely thermal, right? I mean, it's one question why you would become thermal, like why maximum entropy. And then, but your actual question is like what degrees of freedom are entangled so that the entropy locally appears big, right? So the question is not so much why it's maximum, because that's another interesting question, but it's not your question. Your question is, what is it that is entangled to lead to entropy locally, correct?
Yeah, yes, exactly. Yeah. What is it that produces the entropy locally?
Yeah.
Yeah, exactly.
Can I ask a question on this slide?
Yes.
Is there, so how does one know when a hydrodynamic description is a valid description?
That's a good question. So yeah, hydrodynamics is only valid very close to equilibrium. So I don't expect it to work in the initial stages. I expect it to work very closely to equilibrium. So what I want to say is there's some dissipation that's coming from somewhere. The system starts to approach equilibrium at some point. So at some point there will be some hydrodynamic description that's going to be valid if the system thermalizes.
Okay,
And
but
it should be a many-body system, of course.
okay, but like, is there a time scale for which the hydrodynamic description is valid, or is it just valid after a certain time when the system starts to behave like a thermal state?
There is a time scale, but I think it's very specific to your system. Like it's very specific to what you're looking at. For example, in heavy ion collisions, hydro works very, very early on. I think they start running the hydro codes from 0.6 Fermi after the collision. That's super early. And it seems to work very well because what they get from their evolution, they can describe the final state pretty well. Is that what you mean by timescale?
Yeah. Thank you.
Yeah.
Good.
Okay, yeah, and the last point is what I already mentioned on the slide before, to find some optimized renormalization group procedures and coarse graining procedures. For example, in terms of tensor networks that are working in momentum space and that are actually taking into account that your different modes are entangled in momentum space. And if you coarse grain, you should remove those short range correlations. And that's similar to the mirror. Okay, any more questions to that? Okay, then maybe let me briefly say something about the state of the art from a QFT perspective. I know there are also many works about momentum space entanglement and condensed matter. But in quantum field theories, there was this paper by Balasubramanian and van Ramstok, and they computed momentum space entanglement for scalar theories perturbatively, and they looked at 5^3 and 5^4 theories. But it's only a perturbative calculation. Then in our next step, some people from Germany, I think they're in Dresden or Leipzig, yeah, Dresden, they took the prescription and they actually formulated in terms of the Wilsonian effective action at a given scale. And this is a very nice formulation because it's easy to generalize this to either higher order in perturbation theory or to actually do a non-perturbative calculation. And I think it would be very valuable to do a non-perturbative calculation. Because there you could also try to compare to holography. And we put forward a proposal that's only a proposal that should be tested in the future. And we argued that you might be able to compute momentum space entanglement from entanglement in Euclidean time. And about the last point, I'll talk about more today. Yeah. So our motivation was thinking about quantum mechanics. If you think about a double well, then you can tunnel from one of the valleys to the other. You have to go through that barrier. And those tunneling paths, they are instantons, and they are very long in Euclid. They're the very long Euclidean time trajectories. If we start cutting in Euclidean time, then we effectively coarse grain the theory, and at some point you cannot tunnel anymore. You only have that one valley, and it looks like it's at finite temperature. So what we try to suggest in field theory is to compute momentum space entanglement, you take your theory in Minkowskian signature, you Wick rotate the theory to Euclidean time, then you consider some time interval in Euclidean time and you compute the corresponding temporal entanglement. And this temporal entanglement is, according to our conjecture, equal to the momentum space entanglement. So temporal entanglement is in Euclidean signature. Momentum space entanglement is something that has a real-time notion, so it's in Minkowski space. And in particular, the Euclidean time interval tau naught is inversely proportional to the cutoff in momentum space. And what we thought of heuristically is it makes sense if you have some cut in Euclidean time that's starting at the origin at tau equals 0. Then if you have very small Euclidean time intervals, then you can fit only modes with high energy. You can only fit the UV modes into it. If you start increasing the size of the cut, then more and more modes with longer and longer wavelengths fit into that cut. And since these modes are integrated out, this is the time interval you're integrating out, you integrate out the high energy degrees of freedom if you integrate over that Euclidean time interval. And there was also recently a paper by Takyanagi and collaborators. They defined something like time-like entanglement, which is entanglement in real time in Minkowski signature. And our results agree with theirs if we analytically continue. But I'll also tell you more what time-like entanglement is.
One quick question about this. So, I mean, if once you have this Wick rotation, your Euclidean time is just another dimension, right? So it's just this, essentially, it's Kanuta-Klein logic, right? That you have an extra mode in the mode, the extra dimension. Along this extra dimension is compactified, you can have modes with only a minimum certain momentum, right? Is that the argument?
Yeah.
Okay, so the Euclidean time is just basically just an interpretation of the setting.
Sorry, could you repeat that?
So the Euclidean, so you have this extra dimension essentially in the system, and then you sort of reinterpret it as in Euclidean time. That's sort of the opposite way of looking at it, right?
Yeah.
Okay. Sorry, then yeah, please continue.
Okay, one question. Can you, if in your point two, if you, so I understand you have a path integral and a Euclidean strip.
Yeah.
What do you do with it to compute the temporal entanglement?
I'll explain how to compute.
Oh.
Yeah. Okay, but I don't explain how. I'm not going to explain in detail how to do it in field theory. I will use holography where it's very easy. But how you would compute it in field theory is very similar to how you would compute spatial entanglement. You just switch out the notion. So what you called space before, you call time, and what you call time, you call space. So you kind of put your replica along the time direction. And in Euclidean time, there's no problem. You can just rotate into each other.
So you think of the path integral on the strip as the density?
Yeah.
Okay.
Yeah, it's completely analog to the calculation for spatial entanglement. You just switch the notion of what your coordinate is.
Okay. Thanks.
Okay, yeah, then how familiar are you with holography? So I have some slides about ADS-CFT. I wasn't sure if you are familiar with it. We can skip it or I can talk through it. It depends on you.
Very briefly, I mean,
very briefly, I think it never hurts to give a bit like a very high level summary, but you don't have to go into too much detail.
this is partly a holography seminar anyways.
So we have a small crowd today here, but that overlap with people that have a bit of a background.
Okay, yeah, I can mention it briefly. So okay, you're probably familiar with different maximally symmetric spaces in general relativity. We can have a space with positive curvature that's at the Sitter space that looks like this, like our universe. You have a time direction, and along that time direction, you have those circles. So that's a 1+1 dimensional de Sitter space where I have one time and one space direction. And on every point in time, I have that circle, and that circle is expanding as time progresses. I can have flat space, which is also a maximally symmetric solution to Einstein's equation, and I can have anti-de Sitter space, which is this hyperbole like thing. And there I just switch time and space. So I have those hyperbolic arches in the radial direction. And well, to describe something physical that I don't have time loops, I just unroll that cigar so that time is in the circle. And well, what the holographic duality says is that a quantum field theory at arbitrary coupling is dual to quantum gravity in ADS. So those two theories are equivalent. What you set equal is the partition function and the generation function. So you can picture it like this. You have your field theory, which lives in a d-dimensional space, and then you have your gravity theory that has one extra dimension, so it's d+1 dimensional, and it may have a black hole in the interior. And it's really two sides of the same coin. So the both theories are completely equal. Everything you can measure is the same.
But also put in Euro code.
It's Charlottenburg class.
Okay, and it's not very useful in that strong form because we don't know what quantum gravity is, and we can't really deal with quantum field theory at any coupling either. So what you usually take is a large n limit in the field theory and the strong coupling limit. So you have some strongly coupled quantum field theory, and this just corresponds to looking at classical gravity. And you can do a lot of things. You can compute your phase diagram that just corresponds to looking at a charged black hole. You can study linear response and Green's functions by quasi-normal modes. And you can actually compute the full nonlinear real-time dynamics by evolving your black hole in time. And there you can also study thermalization by studying the formation of a black hole in real time. So if I'm in a curved space, then the shortest distance is not really a straight path, but it's some geodesics. And that graphic might look familiar to some. If I want to calculate the entanglement entropy in my field theory, then this corresponds to finding the geodesics or the minimal surfaces in the gravitational theory. And there you can really see the beauty of the ADS-CFT correspondence. So you have some quantum measure here. This is purely quantum. This entanglement entropy doesn't exist in a classical theory. And on the other side, you have a theory that's purely classical. There's no notion of quantum, but it somehow tells you something. It can geometrize your quantum measure. So you have the analog of your quantum measure in a purely classical theory, and you can visualize it. Yeah, this was the very short description. Do you have any questions about that?
No.
Okay, good. Yeah, then let me briefly say what time-like entanglement is. And this was introduced by Takiyanagi and his collaborators. And they were considering the following. So their motivation was in holography, you can study the emergence of space from spatial entanglement. And they were wondering if you can see how time emerges by studying entanglement in the time direction. And what they did is they have a cylinder here. It's a 1+1 dimensional theory. You have one space coordinate, you have one time coordinate. And usually if you compute entanglement entropy, then you look at that spatial cut, which is A, and compute the entanglement entropy on that spatial cut that's living on a fixed slice in time. Now they just rotate the whole scenario. They fix one point in time, one point in space, and look at a cut in time. And that's literally just rotating coordinates into each other. And if you have your standard entanglement, then you usually look at the space-like interval, as I just said, that's between P and Q. And in general, you can write down the entanglement, and in a conformal field theory, it has this form. It's proportional to the central charge, and it's just the logarithm of the distance divided by some UV cutoff. What they did now is they analytically continued this whole scenario to have a time-like interval. So they said that this distance is smaller than 0. And then you don't have an entropy anymore. What you get is a pseudo entropy. So the entanglement entropy is actually complex. And this imaginary part here is just proportional to the central charge. And it's literally an analytic continuation. Your logarithm, you take out an I here, and then you get this imaginary part because of the minus sign. And the last equal sign here is for purely time-like interval. So I fix one point in space, and I look at an interval in time as shown above there. Any questions about that?
Is there any relation between time-like entanglement entropy and the HRT prescription?
And the what?
And the HRT prescription, maximin.
Yes, they looked at that in more detail, and you can in there are cases where it does they show when it works and when it doesn't work. But you can compute it with minimal surfaces if that's what you're asking.
Yeah, thanks.
Yeah. Okay, and there's an equivalent description where you write down your Hamiltonian and then you switch the notion of your coordinates. This is the double Wick rotation that earlier someone asked a question about how to compute it in field theory, and you do this double Wick rotation. So what is time you regard as space, and what was space you regard as time, and then you just switch the notion of your coordinates. And the time-like entropy is a pseudo entropy. That's why it's complex. And it's defined like a pseudo entropy. So it's the transition amplitude between the two states psi and phi.
So it's okay. So it's not a state and it's not an entropy. It's like this. Yeah, okay, I understand.
Yeah.
But formally looks like an entropy.
It formally looks like an entropy, yeah. And actually, if this time interval is not real time, but Euclidean time, as I will use it, then it's an actual entanglement, and then it's an entropy because it's real. Okay, and well, because we used it in our paper, I briefly say something about T-bar deformations. So in QFT, you can understand many deformations, but one certain kind of deformation is very poorly understood, and those are irrelevant deformations, because usually your UV blows up and you can do your usual RG procedure. And one irrelevant deformation that attracted a lot of interest in the recent years, because it's exactly solvable and you can study it, is the so-called T-bar deformation. So here T is the energy momentum tensor. And it looks like this. So you have your CFT and you can deform it by your T-bar operator. So T and the bar is just the holomorphic, you're in holomorphic coordinates, and that's just a conjugate. So basically you're deforming your theory with the stress tensor, and in D equals 2, that's a 4-dimensional operator, and you can derive some trace flow equation. And your deformed theory is no longer a conformal field theory because you introduce some scale, so it's a quantum field theory. And holographically, there was a proposal how to mimic those T-bar deformations, and it's very graphic. So what you do is you just cut off your space at a fixed radial position. So you go from the middle to some finite radial distance, and then you cut off your space. And what you're doing with that is you cut off the UV degrees of freedom. And depending on how you're slicing your space, you might end up with a quantum field theory on a curved space if you don't use flat slicing.
Can I ask a question about this?
Yes.
Having a T-bar deformation, how different is that from just doing an RG flow from one fixed point to another? So I'll tell you what I have in mind. Sure, you know Cardy's C theorem, where you can go from one fixed point CFT to another fixed point CFT, and your central charge varies along this trajectory.
Yeah.
Is there an analog of that story that can be seen here when one does the T-bar deformation on the CFT?
So we argue exactly in that direction, but T-bar deformation is not the same as the renormalization group. People thought like that initially, but it's a different thing.
Okay, but you're saying you can still see remnants of changing central charge when you do a T-bar deformation. Is that correct? Or what is the statement?
The statement is...
You still have your CFT, right? Like up to the
But
deformation.
then it's a QFT because you do a TT bar deformation.
Right, but the IR still looks like a CFT. They can still define things like separate charges, but I guess once you go into the UV, this breaks down, you don't really have separate charge anymore.
Yeah, you're in a QFT and you start integrating out your UV degrees of freedom. It looks like RG, but it's not an RG.
One thing that's always confused me about this construction, maybe you can answer this, is that this cutoff seems to me like an awfully coordinate dependent thing to do.
Yeah.
But the action deformation is varied, right? Like that does not seem to depend on what coordinate system you choose. So where how does the contradiction resolved?
It kind of does because you have the induced metric in here.
Ah, okay.
So
Yes.
yeah, you're right. Depending on what I do here, I can get a QFT on a circle, I can get a QFT in ADS, or I can get flat space, but you will get it in the induced metric. So it also appears in the field theory.
That's what you mean by slicing. Okay, thanks.
Yeah. Okay, sorry, this was very brief, but you can keep asking me questions if it's hard to understand. Now let's get to the temporal entanglement. And again, I asked AI to draw some picture how temporal entanglement might look like. And this is what I got. And before I get to it, so why should Euclidean time be related to RG flow in ADS? And one graphic to illustrate this is the following. So you look at your ADS cylinder and global coordinates. You have the radial direction, that's eta, and Euclidean time is going upwards. And this is dual to some CFT, which is living on that circle here. And the radial coordinate in that CFT, if you choose radial quantization, then this radial coordinate corresponds to Euclidean time. So if I do a dilation, a conformal transformation, then I'm actually changing by an interval in Euclidean time. So now what happens if I do my TT bar deformation? If I deform the theory by TT bar, then I get to that dashed line because I'm cutting off at a finite distance in eta. And that circle here shrinks. So I go, is it clear what's happening?
So that's one RG step.
Yeah.
Or TT bar stuff.
Yeah, or TT bars. Yeah, it's a TT bar step, but it kind of looks like an RG step if you look at the bulk picture.
Good.
Sorry, so in this picture you have like a cap at the bottom, so you have some initial state, or is your
Yeah. You have an initial state.
okay, so the Euclidean time is not periodic.
Euclidean time is not periodic here. Yeah,
Okay,
that's a zero temperature. Okay, so now take your global ADS3 and you can choose global coordinates either by the cosh and sinh here, or you can also choose a radial slicing where those two guys are equal and both calculations yield the same result, but I'm only gonna present to the one in global coordinates. So now we fix the spatial position. That means we can choose phi equals 0. And we look at entanglement in time at a fixed spatial position. Then you can write down your induced metric, and we write it down in Euclidean time, and then we compute the temporal entanglement by finding the minimal surfaces. So you take your induced metric, you write down your area functional, and you minimize it. And the solutions look like this. Even though it looks complex, they're actually real because the argument of the hyperbolic arctangent is always larger than 1, and you could rewrite it in something real. And this eta star here is the turning point of the surfaces somewhere in the bulk, and it's related to the length of the time interval. And I'm going to show that on the next slide. Okay, so those different minimal surfaces look like this. If I choose a turning point that's far in the bulk, then I'm probing large time intervals. if I'm choosing a turning point that's closer to the conformal boundary, then I'm probing small time intervals. And we already know that from spatial entanglement, it's very similar there. If I probe the UV, then I don't need information from deep in the bulk. It's okay if my entangling surface turns around closer to the boundary. While when I'm trying to probe the IR, then the entangling surfaces, they're hanging down very far in the bulk. So what's happening now if I do my TT bar deformation? I cut off my space at some radial position. For example, this brown or orange, whatever this line here. And it's a hard cutoff. It doesn't influence the entangling surfaces. I just lose all the entangling surfaces that are right of the cutoff. So the green surface is still there, while the red surface is already integrated out. And in my effective theory that lives on this slice here, I still can resolve all time intervals, but it's an effective theory with an effective time. So I cannot resolve this red time interval anymore in my effective theory. So I coarse-grained. Is that clear?
Mm-hmm.
Yeah. So it's an effectively coarse-grained theory on that slice here. And you can, if you have the minimal surfaces, it's very straightforward to calculate the entanglement, and it looks like this. It's not very instructive. It's proportional to some central charge. And this R here is the radius. So through the slicing, your theory lives on a circle, for example, which has some finite radius. And this is just the R here. And tau naught is related to the length of your time interval. And this entanglement entropy, it has some symmetry. So I formally get the same entanglement if I I can compensate a larger Euclidean time interval by making the radius of the theory smaller. Making the radius smaller means I have to deform the theory more. So I move the surface further in with the TT bar deformation. So the radius is formally infinite if you have an undeformed theory, and the more you deform, the smaller the radius gets. Because if you're looking at this, you're basically moving in here, inwards. So your circle gets smaller and smaller. And now I have the symmetry. If I go to larger Euclidean time intervals, I still have the same entanglement entropy if I deform my theory more. So if I move further in the infrared. And there's also, you can also derive what's the lowest time scale that you can resolve in Euclidean time. And that's just related to the turning point. So the smallest time scale will be the entangling surface that's minimal here, that's resolving the smallest time interval here. And you can extrapolate it back to the bulk, and that gives you the smallest time interval that you can resolve in your effective theory. If you remove the TT bar deformation and basically you send the R to infinity, then you're taking the limit of being back in a CFT. Then the entanglement entropy looks like this. It's C/3, the logarithm of your effective radius divided by L. And it looks exactly like the entanglement entropy of a CFT at finite temperature. And this is in agreement with our conjecture that integrating over Euclidean time corresponds to a coarse-grain theory at finite temperature. Any questions about that?
So the finite temperature part comes about because your ADS boundary is a circle, and now that you've by the TT bar deformation, it's a circle at finite circumference, right?
What is this? I don't think what is a circle?
So now you're looking at region A in imaginary time, right? That's
yeah.
That goes along your ADS boundary. So if you look at the whole picture of 90 degrees, then the time coordinate relative to that surface is just a circle of the 80th analog and 80th boundary. But you would
it's not infinite.
Okay. That's because that's finite after the TT bar deformation. That's why you have now a finite temperature result. No.
Yeah, it formally looks like it's at finite temperature, exactly.
Exactly. Okay, then everything's fine.
Okay. Yeah, and just 2 comments, that's the end of the results. So we also, so the results so far were at 0 temperature. You can look at finite temperature, and there this symmetry I was talking about is enhanced. Now you have an interplay of temperature, the size of your temporal interval, and the UV cutoff, and you can rotate them into each other, and that you still get formally the same entanglement entropy. For example, you can increase.
Now you completely lost me. I mean, it's the first time you mentioned temperature ever.
Yeah.
Because I mean, you mentioned thermalization earlier, but it meant something completely different, right? That was just an in principle dynamical property that you might or might not have. Now you really take a quantum field theory and take a thermal limit and see what the entropy is doing.
Yeah,
right?
yeah. Here you're completely at equilibrium. There's nothing out of equilibrium.
Okay, and then at least got your point. But then where would temperature come in?
So here we just put a black hole in the interior. That's how or you make your your Euclidean time periodic. That's where the temperature came in.
But your Euclidean time wasn't periodic when you did the TT bar deformation, right?
Yes, on the previous slide, the Euclidean time wasn't periodic when we did the TT bar deformation.
But when you're doing the computation, it is periodic.
When we're doing the
when you're computing the entanglement entropy, is time periodic then when you do the TT bar deformation?
Let me think 1 second. If I go back to my cylinder, I don't think it should be, because it's infinite here. If you move in, it's still infinite in Euclidean time. I know that in real time you have the Poincaré horizons, so there's but I don't think that happens in Euclidean time. Yeah, well, what we got is a lower limit. So you get some. Here you get a requirement on the smallest time scale that you can resolve, but I don't think there's an upper limit.
I see.
Yeah, I don't think there's an upper limit in Euclidean time.
Okay, thank you.
Yeah, and here increasing the time interval, you can compensate it either by decreasing the temperature or integrating out more UV degrees of freedom by moving in the cutoff. And the second point we also looked at is non-relativistic theories. So in relativistic theories, if you go to Euclidean time in flat space, then Euclidean time looks just like a space direction. But if you go to a non-relativistic theory where you have some different factor multiplying your line element, the d tau squared, there the time direction is actually different. And if you compute the entanglement entropy for those at the temporal entanglement for those non-relativistic theories, then the temporal entanglement can actually detect the dynamical Lifshitz exponent z. And this is something that's not accessible from the usual spatial entanglement, because the spatial entanglement doesn't see that at 0 temperature and density. Okay, this was just a comment. Yeah, let me get to the conclusions and especially to the outlook. So our proposal was that tracing over Euclidean time corresponds to coarse graining in quantum field theory. And in particular, that we want to show that temporal entanglement corresponds to momentum space entanglement. And our temporal entanglement is a real valued quantity, unlike the time-like entanglement in Minkowski space, that's only a pseudo entropy. So all those entanglement entropies are real. It's an actual entanglement entropy. And well, the first immediate next step would be to set up the calculation in a. Ideally, you could do a field theory calculation, but it's pretty hard. And I think the next best thing you can do is set up a tensor network calculation. And I don't think that's very hard, because you can set up your tensor network very similar to what you do with the real space entanglement, just at a fixed point in space, and you do the same thing along Euclidean time. And there you have all the techniques to compute the entanglement entropy. You can show that it corresponds to coarse graining. And you can try to derive those improved RG flows. And you can design a tensor network that removes the short-range entanglement between those different momentum modes. So these would be the immediate next steps that I would like to look at.
Can I ask questions about this?
Yeah.
Oh, so many points. Never mind. So I mean, I'm not quite sure in what sense temporal entanglement is the same as momentum space entanglement, because one is of quantum. I mean, of course, morally in quantum field theory it is, because you make. I mean, I understand this, but I mean, technically speaking, one is a complex valued quantity, right? Coming from a time-like quantity, and the other one is an actual, I don't know, it's called a symplectic transform of the setting to a space. So in what way is that the same? And the other, that's my question. And the other question is, why would you use tensor networks to remove entanglement? I mean, isn't it natural to like use mode transformations, like Gaussian, like non-interacting transformations to remove entanglement and not tensor networks?
Yeah. So to your first questions, what did you say is
The
complex?
time-like entanglement.
Yes, but
Temporal
we're looking at the temporal entanglement, and the temporal entanglement is real, just like momentum space entanglement. And the idea would be to show that. So what we want to show is that they're the same thing. So they're both real valued quantities.
I mean, you really want to literally show it's like an equality sign between them in some sense.
That you can, yes, that you can compute momentum space entanglement from the temporal entanglement.
Okay.
In imaginary time.
Yeah, in imaginary time. And your second question, yes, I want to have some procedure where you have basically it refers to the disentanglers, that you disentangle the short-range entanglement when you do your coarse graining.
No, I understand that. I mean, that's mere like association, but I mean, another association that I have is that, I mean, you must know. I mean, it sounds completely unrelated, and I'm just mumbling, but you know that time evolution is hard. Like, well, in quantum information terms, time evolution is as powerful as a quantum computer. It's PQP complete to look at the time evolution of local Hamiltonians, right? Yeah. Then if you do it on tensor networks, then there's problems, as with all other methods. There's the entanglement growth, and you can do this for short times, and then you have to stop because, well, you know all this. That said, if you look at an interacting bosonic system, like of the type that you have, you can go to some times, but you can say, oh, it's a misunderstanding that the entanglement in real space prevents you from going to long times. You should go to a frame where other notions of entanglement matter. Namely, you co-rotate to a mode transformed frame, and then what matters is the entanglement between those effective modes that you then treat with tensor networks.
Yeah.
That's an idea that should even work for quantum computing, although I've never seen this written out somewhere. I'm just saying the idea of making mode transformations, like bosonic mode transformations generated by quadratic Hamiltonians and tensor networks together is an extremely powerful idea.
By mode transformation, you mean Bugler-Bach transformation?
Well, whatever you like. I mean, for you, like quadratic, e to the power of something quadratic bosonic. I mean, then there's so many names for that. Call it Bugler-Bach, yes. I mean, I think that's more like my my gut's feeling that this might be a good framework to disentangle stuff rather than using the mirror picture, because then hell breaks loose because you're breaking all symmetries and whatever. It's not so easy.
But do I understand correctly that in Euclidean time it's easier to do the time evolution than in real time, because it's not a unitary time evolution? If you're in Euclidean time, it's non-unitary, and
But,
it's.
I mean, if you, for example, use a mirror and use a mirror, the moment your tensors are no longer unitaries,
You also have problems because then they're not canceling, and then this nice property that you can just like remove U daggers is also gone. I mean, you can think of mirrors with non-unitary time evolutions, but then hell breaks loose for other reasons. I mean, there are ways of doing that, but it's not so easy.
Okay.
So at the end, well, I notice you have a question mark there on temporal entanglement for qubits. Also, when you talk about the Minkowski entanglement being imaginary. Okay, so that 10 years ago, when I was doing my PhD with my advisor, we wrote a series of papers looking at field theory in Minkowski spacetime. And so, like in the 1+1D, people really tend to study what's called the Unruh effect, like these entanglement between the Rindler wedges in spacetime.
Yeah.
And so what we showed is that if you rotate, when you write the field modes from, say, an accelerated observer, the Minkowski vacuum for an inertial observer looks like an entangled state. And we showed that if you rotate, you can do exactly the same thing looking at the future and past light cones. So we introduced a notion of like time-like entanglement. And we showed that like you can extract it, you can turn it into space-like entanglement. Well, actually, so this was all done by people before me. My thing was we wrote a paper where we entangle that we show that, you know, so a detector at a single spatial location is entangled at 2 different times, and you can use this to do what we can also have it at 2 different spatial points, and you can use time-like entanglement as a resource to do like quantum key distribution things. And we also proposed like how to actually experimentally measure this in real life, where so the analogy of acceleration for time-like entanglement is, you can imagine like ramping the energy gap in a 2-level system or something like this.
That sounds pretty cool. Maybe you can send me those papers because I'm not aware of it.
Yeah, okay, sure. I can, yes, but so that's, I just don't understand. But okay, so in our sense though, time-like entanglement entropy is completely real, and you can measure it, you can use it for industrial purposes. I don't know what being like. Sorry, there was a thing on a slide ago, which is like in Minkowski space, the temporal entanglement is imaginary. Well, our temporal entanglement is it is exactly in all ways the same as spatial entanglement. Basically, operationally, you can use it to do everything you could do with spatial entanglement.
I also don't think you calculate the same thing, right?
Perhaps.
I think you guys are just using the same term for different mathematical calculations.
Well, I just mean, like, you know, you have a detector, which I guess is just some modes localized in, you know, packets in time and space. But I think about it as a detector in this setting, or just an unrooted weight detector. Sure, that being simpler at place and space time, and then you can calculate the response, and you see it thermalizes and that thermalization. Well, you can compute entanglement entropy.
But you compute between the detector and your fields, right?
That's right. So
She's computing entanglement between modes of the fields with themselves.
well, no, sorry, no. This is entanglement between modes of the field. You just copy your detector to see it, but the field modes are entangled. It's like, I mean, because it's just a Goodie-Bug. It's the same Goodie-Bug transformation as the Rindler wedges. So what you have is a 2-mode squeeze back for the quantum expands in like 1+1D flat Minkowski space. I mean, obviously here you're also considering way more like things that are not just Minkowski space down, of course, which is the whole point. Okay, anyway, yeah, all right, maybe I'll send you some.
Yeah, thank you.
Very good. I can also send you the mode transformation papers. Yeah.
Yeah, that would be great.
We even tried this in actually, to say that we even tried this in quantum field theory. I mean, we had an old paper on time evolution and another one on fermions, whatever, but we tried this now on quantum field theory, and this is like super important. In fact, the method was not really working without proper mode transformations nowadays.
Okay.
Anyway.
I have a question, like, do you have an intuition, kind of a CFT should be scale invariant, right? So in what sense does one see this in momentum space? Like, in what sense is a CFT different than not CFT? I would just imagine that kind of there should be something special in the CFT that makes it scale invariant in momentum space. So
There should be something special about the CFT in what sense?
I just okay. You've cited this paper from the Dresden people. I talked with one of them, and he looks at something similar. And he, for example, I think told me that in a CFT, the momentum shells in the vacuum state are not entangled with each other.
In an interacting CFT or in a non-interacting CFT?
This I don't remember. So I was wondering whether there's something you can say about what how you see scale invariance of a CFT in momentum space.
Okay, I haven't thought about that, but it's pretty just related to your usual scale transformations. I think it would look pretty similar to the dilations to your scale transformations that you can do. So if you talk about large, you should relate it to something.
And the last question, temporal entanglement for qubits. Well, I should kind of put the usual happy sauce on top and then see what happens. No?
Yeah.
Time special. I mean, that might be a good idea.
I have two questions on your previous slide. The first, so the first question is this proposal of yours, which in which you're trying to relate the temporal entanglement entropy to momentum space entanglement.
Yeah.
Do you think it is reasonable to extend this proposal to not only the von Neumann entropy but also the relative entropy?
What do you mean by relative entropy?
Oh, well, in quantum mechanics, the relative entropy is a measure for two quantum states, rho and sigma, and it's trace rho log rho minus rho log sigma. So the von Neumann entropy is a special case of the relative entropy if you take sigma to be the identity.
Yeah. What I would try to look here instead would be Renyi entropes, because I'm not sure if I couldn't. I would look at Renyi entropes and see if I can extend something there in that direction.
Right.
For the time-like case, for the time-like entropy case in this Takanagi proposal, I mean, there you do in fact have this, right? Like the proposal is that you have two states, and you get like some pseudo entropy, which in some cases is not really the relative entropy, but it's something similar. It tells you about sort of the overlap between two different states.
Yeah, exactly. It's a transition amplitude from one state to the other.
I see. And the second thing is this TT bar transformation. Do you know of anyone who's looked at sort of a TT bar transformation on the level of a lattice? Because arguably, I would think that is easier to do than doing it in a tensor network.
I'm not sure if people looked at it on the lattice, but you can derive your energy momentum tensor for your lattice theory, and then you can do the deformation. So I don't think there's a problem doing that. But I'm not aware of any works doing that. We were thinking about doing it in that direction when we tried to compute the temporal entanglement for some more general classes of theories. And the first thing that came to mind is to look at some lattice field theory where you can just put it on a computer. It's very easy to compute entanglement there if you set it up, if you discretize in the Euclidean time. But I'm not sure if someone looked at the TT bar deformation for lattices so far.
No, there is work by, I mean, I think I know one paper.
Really, TT bar on the lattice.
Yeah, they didn't okay, let me check.
Oh, I would be very interested in that.
There's a paper TT bar deformation and lattice approach.
Oh,
That's
Who's it by?
Is it by
From December last year. So.
by the Cologne people? By Nele?
No. Some Asian name,
Ah,
China.
I see. Okay. Anyway, I meant
Why are you asking about the lattice?
I don't know, I didn't ask.
No, I was asking about the lattice because you wanted to compute this temporal entanglement for a tensor network, and once it's just done on a regular lattice, then it's just easier to see what you would need to translate for a tensor network.
Yes.
That's why I was asking.
It's also much easier to see the coarse graining, at least for me. If you have some interval, for example, if you think of it as spins, you can just integrate out your spins. You coarse grain. You go from a finer lattice to a more coarse lattice. It's much easier to see than in a continuum theory.
So actually, I have another question. It's a bit broader. So if you think about entanglement entropies, there are all these relationships between bounds between entanglement entropy and correlation functions, right? Because, for example, mutual information upper bound to like 2-point correlations.
Yeah.
Does something similar exist for these time-like entanglement entropies as well?
I'm not sure. I'm not sure. I think someone looked at correlation functions.
I guess because at some point you talked about some exponents. So I was wondering if there's any relationship between O-talks, for example, and this.
But this one bounds surely the other. I mean, that's just basically Hinsker's inequality would do this. That's right.
Yeah. Yeah, I'm not 100% sure, but I think Song he started exploring that, but I'd have to look it up. I'm not sure.
Cool. But yeah, okay. What I meant, Neil was college about was thinking about this, but I'm not sure whether that's a paper. But I know that she's still thinking about this. Cool, nice, lots of things, food for thought. Very good. Are there any further questions for now?
Not really. I guess I would just probably. Well, okay. I can send you one paper by Hoofer Vidal in which he contrasts momentum space renormalization with real space block spin renormalization.
Yeah.
And that is the only paper that I know of, and like from him, which tried to construct a tensor network for momentum space renormalization.
Yeah, thank you. That would be great.
Right, thanks.
But I will also send the papers I mentioned.
Yeah.
So we're talking about papers, that reminds me.
No, everybody's telling no, I'm not more than most of them.
No, so there's one paper a while ago where people talked about mirror actually in this kinematic space formalism, right?
Yes.
I was just thinking of that because you were saying that naively in the mirror, you do not have any mixing of entanglement between different scales. But of course, if you say that the boundary of the mirror is not really a physical space, but some other space, like this kinematic space, for example, of geodesics, then once you do transformation to real space, you might naively also end up with some momentum space entanglement, right? So just something that just popped into my head.
No, I see that. Yeah, I mean, also we should. Philip might be interested in this.
Oh yeah,
from the removing short range entanglement, because that whole thing is. I mean, you first remove k minus k paired entanglement by hand, and then you with an algorithm remove short range entanglement. One day I want to run this on the quantum computer and dequantize quantum algorithms with mode transformations. That's what happens. But that's not for today. Very good.
Right.
And thank you very much indeed for this interesting talk.